Hello everyone. We are now ready to start your second chapter of your NCRT, which is named Units and Measurement. In this chapter there are mainly four topics, that is your fundamental units and derived units, dimensions, significant figures, and error analysis. Out of these four topics, you may have some idea about the fundamental units and derived units, but the second, the third, and the fourth topics are completely new for you guys. So I'm going to divide these four topics into four videos. And in this first video, we are going to look into fundamental units and derived units. In this video, you are going to learn basically these four topics. That is your physical quantity, the units that we use for your mass, length and time. Then we are going to look into something called fundamental and derived units. And finally, we are going to look into measurement of large distances. Before we go into physical quantity, let me tell you what is a quantity for us. The definition of a quantity is anything that we can measure is what we will call it as quantity. For example, if you measure time, say the duration of a movie is 2 hours, then you are making a measurement of the duration or the time. Hence this time is a quantity for us. You are measuring your height, how tall you are. This height of yours, I can say is again a quantity. You can measure how hot, how cold is the temperature today, and that temperature measurement is again a quantity for us. Similarly, you can have measurement of area, which tells you how much space has been occupied by a shape. So your area is also a quantity for us. Then you have volume. Again, you can see it can be measured. So you have a quantity called volume. You can measure length. You can measure radius of a circle or of a sphere. You can measure speed with which a body is moving. So again, your speed is a quantity. You can measure how much matter is present inside a matter. So your mass becomes a quantity. You can measure weight. You can measure force. That is how much is the push or the pull on a body. You can measure the velocity, which represents the displacement of a body in a given time. So again, your velocity is a quantity. There's something called momentum, acceleration, and many other quantities which you can measure. So what is a physical quantity? Now any quantity which appears or which we use in describing the laws of physical phenomena or a principle will be known as a physical quantity. For example, suppose we write Newton's law, where you have force equals to mass into acceleration. We are expressing Newton's law using these three different quantities like your force, mass and acceleration, and I can call them physical quantities. Similarly, you have Newton's law of gravitation. You have force, you have gravitational constant, you have mass and distance. So all these quantities that we have here will be termed as physical quantities. Then we have expression for kinetic energy, where we write half mv square is equal to kinetic energy. So the mass and the velocities, we can start calling them as physical quantities. Similarly, you have potential energy, which is given by mass into acceleration due to gravity into height. So all of them, they are physical quantities. So to tell you again, a quantity which appears in any physical laws, the quantity which appears in an equation which describes any physical law will be termed as a physical quantity. Now just as I told you, a quantity is anything that can be measured. A physical quantity is also something that can be measured. The idea behind measurement is simply that it is a process of comparison. To make it clear, let me show you what is the meaning of measurement is. Suppose I use a scale that is 15 centimeters long. That means starting from this mark here, which is a 0 centimeter mark, up till this mark, which represents your 15 centimeter mark, which you are familiar with, you will see these divisions or the lines that are there in this scale, and these divisions help us to make measurement. Now in this scale, if I start from this end of the scale till here, I can say it is 1 centimeter mark. That means the distance from here to here, we know it is 1 centimeter. Now, what we do with the scale is that we measure the length of something. So let's say if I want to measure the length of this pen, and I use that scale that we have, and I see that I keep the tip of this pen onto the 0 centimeter mark, and the end of this pen is found to be somewhere here, that is after your 6 centimeter mark, let's say 6.1, 6.2 and 6.3 centimeter, then I have to tell you that the length of this pen is 6.3 centimeters. If you remember, your 1 centimeter was the distance from here to here. If I take another 1 centimeter, the total distance I have to call it 2 centimeters. If I take another 1 centimeter, the total distance becomes 3 centimeters, and so on. In this case, or in this example, I can tell you that the length of this pen is 6 centimeters, which is 6 times of centimeters plus the 3 divisions that we have for every centimeter, that is a 0.3 centimeters. So clearly you can see the pen, I can tell you, has a length which is 6 times more, or let's say more than 6 times of every 1 centimeter. So clearly if I ask you which has more length, 1 centimeter or the length of this pen, you have to say that the length of this pen is longer compared to 1 centimeter. So clearly we are comparing 1 centimeter with the length of this pen, which is found to be 6 times, or let's say 6.3 times that of 1 centimeter. Same thing happens when you go and measure mass. Let's say I have a block which is 1 kg, and suppose if you buy a vegetable which is, let's say, 10 kg, it simply means the mass of this vegetable is 10 times the mass of this 1 kg. So basically here again we are comparing the mass of these vegetables that you have bought with the mass of this block, and that is found to be 10 times greater than this block, and again you can see we are comparing the mass of this vegetable with the mass of the block. So measurement again is a process of comparison using suitable scales or devices and using suitable units. The centimeter here is what is known as a unit for us, and every measurement should have some units. Now unit also means 1, and unit is so important. As you can see here, we have expressed the length to be 6.3 centimeters, such that this centimeter was the unit that we have chosen. And if we write 6.3 without a unit, it is totally arbitrary and very much unspecified, such that this has no meaning for us. So the measurement is incomplete without a proper unit, because without that unit, we do not get a proper idea of how much is the measurement is. A unit definition is an arbitrary chosen standard of measurement of for any given quantity. Now centimeter is not the only unit that we use. We may also use units like kilometers. Now the reason why we need kilometer is that every time we may not be measuring something small in length, but we might be measuring something much longer. So we need a bigger unit of length, and that is what we have, a kilometer. Similarly, if I measure a time, we can measure small durations of time in the units of minutes, which you are familiar with. But if I have to measure a longer duration of time, I'm going to use bigger units like a month or years or days. Similarly for mass, commonly used units are your kg, but if I'm going to measure something small in mass, I'm going to use units like your gram, which is the smaller unit for measurement of mass. Some other common units of other quantities are, suppose we are measuring temperature. You can see in this device, that is your thermometer, you have markings or scales or divisions where you have 0 degree Celsius, here it is 50 degrees Celsius. So if I ask you what is the unit here, I'm going to say that the unit that you use is your degree Celsius, such that each divisions that you have here, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, all these divisions actually represents 1 degree Celsius. So from 0 degree Celsius to 50 degrees Celsius, you have your 50 divisions that can tell you the temperature between 0 and 50 degrees Celsius. In the same scale, you can see on the other side, you have another scale which is not your degree Celsius but Fahrenheit scale, which is also a scale used to measure the temperature, such that the divisions here that we have are not your degree Celsius divisions, but each division here represents 1 Fahrenheit or 1 degree Fahrenheit. You also have seen we can measure angles, and using a protractor which has all these divisions around it helps us to calculate the angle. For example, if I have a line which is in this line coinciding with the 0 mark, and suppose we have another line at this point somewhere here, clearly you can tell me the angle measured by this protractor is 90 degrees. This degree here helps us to measure the angles, and this degree is the unit of your angle. That means going from here till here, we have 10 divisions, 6, 7, 8, 9 and 10, and this 10 division here represents 10 degree, such that each division here represents 1 degree. So the value of each division, we are going to call it 1 unit. So far what you have learned is that we have quantities, which we call them physical quantities, that we can measure, and whenever we measure a physical quantity, we do so using a proper unit, such that for mass maybe we may use kg or gram, for length we may use meters or centimeters or kilometers, Then we have seconds or hours or days or even years for time. Simply writing the measurement as 10 for mass does not give a proper idea of what we are talking about, so it has to have a proper unit along with it. And simply writing 10 for length also doesn't give a good idea about what we are measuring or how much is the length, so it should follow with a proper unit. That means unit is a very important part of any measurement. Now as such, the unit of this mass, length and time, these are very basic unit or basic units that we may have, that we may use in measurements, and we call them as fundamental units. In the early days of physics, knowing the units or using the units for these three quantities were enough because mainly we were talking about motion, which involves the measurement of mass, length and time. But as we move into time, we realize that there are other branches of physics like heat and temperature. You have optics, you have sound and so on, and there was a need to have more fundamental units apart from these three, which are very much used in the other branches of physics. As such, in the new system, which we call as SI system or Internationally Adopted System, which was formed in around the year 1971, we came up with 7 base fundamental quantities or basic fundamental quantities. The first one is mass, second one is length, third one is time, the fourth one is temperature, fifth is electric current, sixth is luminous intensity, which means brightness, and finally we have seventh one, that is your quantity of matter. These fundamental quantities in your SI system, which is your internationally adopted system, we are going to use the unit kilogram for your mass, meters for your length, seconds for your time, Kelvin for your temperature, amperes for your current, candela for your luminous intensity, and mole for your quantity of matter. That means if you're following this international system, we are going to express our mass in kilograms always, length in meter always, time in second always, and so on. That means even if somebody writes mass of 1000 grams, that means if we write a mass of 1000 grams, we are using a system where we have gram as the unit but not kilogram. That means this is not the SI system. If we write the same 1000 gram as 1 kg, which is no different than your 1000 grams, I can say we are using the SI system to express the same quantity or the same amount of quantity, but we are following a unit, that is your kilograms, and that belongs to your SI system. Now luminous intensity, which means candela, short form is CD. It simply represents, if I write 1 CD, it means 1 candela. If I write 2 CD, it means 2 candela, and so on. 1 candela simply means the brightness equivalent to the brightness of 1 candle. Therefore, 2 candela means brightness equivalent to the brightness of 2 candles, and so on. And to measure the quantity of matter in SI system, we use mole. This 1 mole simply means there are 6.023 into 10 to the power 23 number of particles that we are talking about. That means if I write 2 moles, which simply means double of this number. If I write 3 moles, it means we are talking about 3 times this number. Now apart from the 7 basic fundamental quantities that we have in your SI system, we have 2 more supplementary physical quantities, which are your plane angle and solid angle. Plane angle in SI system is always measured in units of radians, which we write RAD, and there is something called solid angle, in which we use the unit called steradian, that is your SR in short. Now this angle theta, which is a plane angle here, such that this is a circle here, is the angle made by this arc, which has a length of S, and the radius of the circle is R. To find this angle, we simply write length of the arc, that is your S, we divide it by the radius of the circle, that is your R. However, in the case of solid angle, we may use a symbol like your omega, which is defined as, suppose we have a sphere, such that we take not a curve, like in your first case, we take an area in this sphere. Once we take that area and divide by the radius square, we get something called a solid angle, and the measurement of this solid angle is in the units of steradians. Now, one of the advantages of using the SI system is that we use prefixes, which are simply the submultiples or multiples of a given unit. For example, we have meters, we have kilogram, and then we have your seconds as the units in your SI system. If I'm talking about smaller units of kilogram, the smaller units of kilogram will be simply a gram, or I can even write DC, which represents your decigram, or CG, centigram, or mg, which represents milligram. Ng can also represent your nanograms, and so on. This gram over here, we've used a prefix called decigram, which stands with the short form D, such that it simply means I'm talking about 10 to the power minus 1 grams. Centigram simply means 10 to the power minus 2 grams. Milligrams 10 to the power minus 3 grams. Nanograms represents 10 to the power minus 9 grams, and so on. Same thing can happen with a meter. We may use prefix like cm, where c represents again centi, mm, which represents millimeter, nm, which represents nanometer, and so on. So you see we have prefixes like c, m, and n, just like we had here c, m, and n, and so on. Now these prefixes simply mean here we have centimeter, that is your 10 to the power minus 2 meters. Millimeter means 10 to the power minus 3 meters. Nanometer means 10 to the power minus 9 meters. We can also have that with your seconds, such that we can write ms, which will represent your milliseconds, which represents 10 to the power minus 3 of a second. Now the meaning of these prefixes is that if I take 1 meter and divide by 1000 or 1000 units, we get a very small part of that meter, and that is what is known as your millimeter. That's why you can see I have 1 meter here, and this 1000 can be written as 10 to the power 3, such that it is 10 into 10 into 10. That's why we get it as 1 millimeter. Now this same 10 to the power minus 3 can be taken up here and can be written as 10 to the power minus 3. With this meter we can write here 10 to the power minus 3 meters, and that is simply your 1 millimeter. So suppose we have 1 meter divided by 100, that means 100 equal parts of 1 meter, then each part that we get after this division, we call it as centimeter. Which in other words we can write 1 meter divided by 10 to the power 2, which is your 1 centimeter, or we can write 10 to the power minus 2 meters, and that is your 1 centimeter. Let me show you the last one, which will make everything clear for you. Such that suppose we have a 0 centimeter mark, and here we have 1 centimeter mark. We have 10 divisions, 1, 2, 3, 4, and 5, 6, 7, 8, 9, and 10. So you can see we have 10 divisions starting from your 0 centimeter to 10 centimeter mark. So clearly I have divided 1 centimeter into 10 equal parts. So when I divide this, I do not get 1 centimeter, but I get the 1/10 of that centimeter. And this 1/10 of a centimeter, we have to write 10 to the power minus 1 centimeter, which you know already, we call it as 1 millimeter. So you can see, so what you have learned just now is that we can use prefixes, submultiples and multiples of any quantity. And just now I've shown you how do we use small prefixes, that is your submultiples. But suppose we want to use multiples in your SI system, again it becomes very easy for us. For example, if I have meter, if I write the K in front of it, it becomes kilometer. If I have gram in front of it, if we write K, it becomes kilogram. This kilometer simply means 10 to the power 3 meters, or equal to 1000 meters. So every time you see a kilo, it's like you're multiplying by 1000 or 10 to the power 3. Similarly, I can have other bigger multiples like your 10, which we call as deca, dA. If we have 10 to the power 2, we call it hecto. If we have 10 to the power 3, we call it kilo. If we have 10 to the power 6, we call it mega. Mega also stands for millions, you can think of, because millions has 6 zeros. So we have 10 to the power 6. Then we have something called giga, which is much bigger multiple. That's 10 to the power 9. We represent by capital G. Then we have tera, that is a capital T. We represent by 10 to the power 12, and so on. That means if I am writing, you may have seen in computers we write gigabyte, that is your GB, it simply means we are talking about 10 to the power 9 of bytes. So what you have learned just now is that if I'm writing centimeter, it simply means I'm talking about 10 to the power minus 2 meters. If I'm writing kilogram, I simply mean 10 to the power 3 gram. If I'm writing kilometers, I simply mean 10 to the power 3 meters, and so on. So these prefixes becomes very easy for us to understand the value of a given quantity or the unit that we are using. Let's move on to learn about the measurement of angles. Now you have seen, if you use a protractor and measure the angle between this line BA and CB, we get an angle of 90 degree at this point. That 90 degree, the unit used with our protractor, as you saw, is your degrees, and this 90 degrees simply means 90 times of that 1 degree that we have here. In SI system, we concentrate more on the units called radians of an angle for a plane angle, and that plane angle we represent in terms of pi. We call it pi radians, and this pi simply is a number which is 22 by 7. Now this pi is defined as the ratio of the circumference of a circle, that is your 2 pi r, divided by its diameter, that is your 2r. And we have seen for any circle of any radius, we get it equal to 22 by 7. That means if you take a smaller circle or if you take a bigger circle, and if we divide the circumference of those two circles by their corresponding diameters, we are always going to get a number that is a 22 by 7, which we round it off to 3.14. Now, when we talk about radians, we say pi is equivalent in talking about an angle called 180 degree. So this is what we use. So what is pi angle? Pi radians for us simply means an angle of 180 degree. So you can see here we have 90 degree. 90 degree is the half of 180 degree. So in terms of radians, I must write it as pi by 2, which you have done in your lower classes. That's why your 90 degree, we write it as pi by 2. So whenever we are following the SI system, make sure that you do not write 90 degree, but instead you write pi by 2 radians. Here we have some more angles. So just now you saw, pi for us represents 180 degree. This degree is not the SI system, but this pi is the unit in SI system. When I take the 90, I can write 180 by 2 to get the 90. Writing 180 by 2 is simply writing pi by 2. So your 90 degree is equivalent to your pi by 2. Then we have a 60 degree, which we can get by dividing 180 degree by 3. That is simply your pi by 6. 30 degree is 180 by 6, so we can write pi by 6. 45 degree is your 180 by 4, so we can write pi by 4, and so on. And of course, if I write 2 pi, it simply means 2 times of 180 degree, which is equal to your 360 degree. So just now what you have seen is that we can represent angles, and the radians is related to your degrees by this equation, which is pi equals to 180 degree. Now, every time we may not measure angles like your 1 degree, 2 degree, 30 and 40 degree. We may measure very or much smaller angles, for which we need much smaller units. For that we have two very small units of measuring angles. We call them arc minute and arc second. Arc minute is represented by this dash here, and arc second is represented by 2 dash that we must write with a number. Such that 1 arc minute means you take the 1 degree that you have and divide it 60 times. So you're going to get a very small angle, and that small angle is what is known as arc minute for us. In this diagram you can see, suppose I draw for you this angle here between these two lines is 1 degree, such that I'm dividing this whole angle into 60 parts. Then this small angle here that we get, which is one part of the 60 divisions, this small angle here, we are going to call it arc minute. That means you have 1 degree here, you divide this 1 degree into 60 equal parts. The one part that you get out of all the 60 divisions, it is what is known as 1 minute. So you can already see it's a very small angle that we are talking about. So arc minute is a submultiple, or let's say not submultiple, but let's say smaller unit of angle. Now we have arc second. Now arc second is much smaller unit of angle, which we get by taking this arc minute and taking that arc minute and dividing into another 60 parts. So just imagine this small arc minute that we already have divided into another 60 parts, and then you take the small part or one part of that 60 divisions. We start calling it as arc seconds. So here we have 1 minute or arc minute is simply 1 degree divided by 60, very small angle. Then we have arc second, which is your 1 minute divided by 60, which is equivalent to writing 1 minute or arc minute can be replaced by 1 degree by 60, and then we have another 60 which we divide, so we have here another 60. So if you take your 1 degree and divide by 3600, you are going to get a very small angle that we all call it arc second. So for conversion, we simply mean here 1 arc minute is simply 1 degree by 60, 1 arc second is simply 1 degree by 60 into 60, which we write as 1 degree by 3600. One more important thing that we may require is that we may want to convert degree into radians or radians into degrees. For that we simply use pi is equal to 180 degree, or we can write 1 radians is equal to 180 by pi degree, or I can write 10 radians is equal to 180 by pi into 10, and the answer will come out in degrees. So see, this is the formula we are going to use to convert any amount of radians into degrees. If I ask you how much is 32 radians, you're going to write 1 radian is so many degrees, 32 radians must be 32 into 180 by pi degrees. So you have converted your radians into degrees, because on the right hand side you're going to have a degree unit. Similarly, I can also write 180 degrees equal to pi radians, which we can write 1 degree equals to pi by 180 radian, which means 1 degree is equal to pi by 180 of radians. Pi is again here 22 by 7 or 3.14. Now next, if I want to find how much is 32 degree in terms of radians, we simply need to use this and write 32 degree must be equal to 32 times of this formula here, that's your pi by 180 radians into 32, of course, and no degrees, you cannot use degrees. So this is how you are going to convert your degree into radians. Just now you have seen how we have measured angles, which may be very large or may be small, using the units like your radians, degrees, and so on. Now we are going to learn very large units of length, or we also call them practical units of length, such that if I tell you to measure the length or breadth of a paper or a book that you have, your centimeter scale is very good enough. However, if I ask you to measure the length of a road, the road is quite long, and using a centimeter scale to measure that big long road is very much not advisable. So you need a bigger units or bigger scale, for which we use kilometers. Now imagine you are measuring the distance between sun and the earth. What happens is that even your kilometer, which was a good enough unit to measure the length of a road, becomes a very small unit, because the distance between the sun and the earth is quite large. For that we use a different unit, which we all call it astronomical unit, short form AU. And your AU simply means the average distance between the sun and the earth. So the definition of AU is the average distance between the sun and the earth is what is known as astronomical unit. Now the value of this astronomical unit is 1.496 into 10 to the power 11 meters. So you can see already it's a very big distance. So many times or multiple of meters. It's a quite big unit compared to meters. If I tell you 2 AU, you simply can understand I'm talking about the distance of about twice the size or twice the distance between Earth and Sun. 3 AU simply means 3 times the distance between Earth and Sun. For example, Earth and Jupiter, they have a distance of 4.2 AU, which simply means that Earth and Jupiter are 4.2 times in separation compared to the separation between Earth and Sun. So obviously the distance between Earth and Sun is less, and Earth and Jupiter is quite large. So you can see we can have more multiples of this or factors. So if I write 10 AU, I simply mean that the distance we are talking about is 10 times the distance between Earth and Sun. So you can see already AU gives a very nice idea behind how much distance we are talking about when we talk about very large distances. Now this AU again is found to be smaller because in physics we may measure distance between two galaxies which is quite large compared to the small unit that is your AU. So we unit very much bigger units compared to this AU, and one of them is your light years. So though we call it light year is not a distance, it's not a unit of time, but light year is a unit of distance. The definition of light year is that it is simply the distance traveled or covered by light in 1 year. That means let's say light starts today or right now from a source and it continues to move with a speed we know is 3 into 10 to the power 8 meters per second. If light continues to move with this speed, which is a very high speed, in a time of 1 year, this light is going to travel a very large distance, and that distance covered by this light in 1 year is what we are going to call as light year. To calculate the distance traveled by light year, we use this formula, which is simply your distance equals to speed into time, where we have to take the speed of light and multiply the time for which the light is going to travel, and we are going to get the distance which the light is going to travel in so much time. So we have said 1 light year, which is the distance, must be equal to speed of light times the time. Speed of light we have written is 3 into 10 to the power 8 meters per second. Time is 1 year. We have converted into days, because you see here we have time units. Second is your time unit, even days is your time unit, or let's say years, but they are not matching right now. They are going to get cancelled, so we have to make them in the same form. This 365 days or 1 year, we write for each day we have 24 hours, so the days are replaced by 24 hours. 1 day has 24 hours. 365 days will have 365 into 24 hours. So we are simply using unitary method here right now. Then we have every hour. So we write 24 here, but every hour is replaced by 60 minutes. And then finally, we have the 60 here, 24 here, 365 here. Every minute we replace by 60 seconds. So you can see all of this time, we started with 1 year, then we have 365 days, and so on. We finally reach a unit seconds, which is a very small unit of your time. This seconds now gets cancelled with the second inverse. Second inverse into second is going to give you just 1. So now we simply have meters, and that meters is a unit of distance. Once we calculate all of these numbers that we have, we get 9.46 into 10 to the power 15 meters. You can already see 1 light year is a very big distance, which corresponds to the distance traveled by light in 1 year. So if I say a person is 1 light years away from the other person, it simply means if a light starts from one person, it's going to take 1 year for the next person to see that light. But for you, for the time being, just remember there are 2 very big units of distance. One is called 1 AU with a value of 1.496 in 10 to the power 11 meters. And then we have the next big unit of distance, that is your 1 light years, which is 9.46 into 10 to the power 15 meters. Now we want to write a relation between light year and AU. It simply means 1 light year is equal to how many AUs? Because we know we can write 100 centimeter equal to 1 meter. So we wrote a relation between centimeter and meter. Now we want to write a relation between how many light years or how many AUs corresponds to 1 light year or so on. For that, we simply write 1 light year and divide it by 1 AU. When we do that, we have the numbers in the same units, that is meters. 1.496 can be approximately taken as 1.5. When we divide this number, we are going to get 6.3 into 10 to the power 4. That means 1 light year divided by 1 AU is so much. Or I can do this, I can take 1 AU right here such that I get 1 light year is equal to 6.3 into 10 to the power 4 AU. or we can simply write 63,000 AU. So let me show you what this number really means. So we got 1 light year is equal to 63,000 times of AU approximately. So what does this means? So what does this really means is that if I take the sun and then take the earth, we know the distance between them, we call it 1 AU. And if I talk about 1 light year, it means I'm going to take this distance that I have of 1 AU 63,000 times, and that big distance that we get, cannot even imagine how big it is going to be. So you see, after taking 63,000 times of that distance AU, we are going to start calling that as 1 light year. So you can already see light year is a very big distance or very big unit of distance. Then finally we have a much larger distance or unit of distance, which we call it as parsec. Now what is parsec? A parsec is defined is the radius of an arc, the arc being 1 AU long, such that this arc at the center subtends an angle of 1 arc seconds. So I'll read the definition and explain to you again. Parsec is nothing but the radius of a circle where an arc of the circle 1 AU long subtends an angle of 1 arc second. It simply means, suppose I have a circle, a very big circle. We have the center of the circle and we have taken the arc on the circle, which is 1 AU. Let's say from A to B is 1 AU. And you can imagine already that this is like the distance between the earth and the sun. So you have taken a very big arc in this circle, and such that I have a very small angle made by this arc at the center of the circle, which is simply only 1 arc second. To give you the real picture, the diagram is going to look like this, such that the 1 AU will start appearing very small, and this is simply a 1 arc seconds. So this radius here that we are talking about is what will be called as 1 parsec. Now we want to find out how much is 1 parsec. To use or to find 1 parsec, we use this formula that you have learned in geometry, that if we have your arc of length L, we have a radius of a circle R, and we have an angle here called theta, which always we have to write in radians, then the relation between these three quantities is that this theta that we have is always equal to length of the arc divided by the radius of this circle. And remember, you can use this anytime you want, provided you measure the angle in radians and not in degrees. So here we have, in this example also, this is your theta angle, but it is given in as arc seconds. So first we convert the arc second into degrees by dividing it by 3600, and we know every degree or 1 degree can be written as pi by 180 in radians. So we have converted your degree into radians. Now everything that we have here is simply your angle that is measured in radians. Once we have the angle, we are going to use the formula, that is your angle is equal to length of the arc by radius. So we are L by R, or simply from here we can write R is equal to L by theta. In this example, or in this definition of parsec, the L is simply 1 AU. So we write 1 AU. The theta is 1 arc second, which is this much in radians. And then we write the corresponding values of 1 AU in meters we have written. And this is the value of this part here, which is your pi is 3.14 and so on. When we solve this, we are going to get so much meters, and that is what we are going to call as 1 parsec. So clearly, if you note, the power here is 10 to the power 16 with parsec, with the light year is 10 to the power 15, and your AU has 10 to the power 11 as the power. So clearly I can say parsec is a bigger unit, or let's say 1 parsec is greater than your 1 light year, and your 1 light year is greater than your 1 AU. Now again, if you want to find how many AU will be equal to 1 parsec, you simply do this. You take 1 parsec and divide by 1 AU. Write the value of AU in meters. write the value of per sec in meters, divide those two, you get a number, you get meters also cancelled. So 1 per sec will be equal to so many times of 1 AU, just like we have done before for your light year and AU. Now after we have learned what are the larger unit of distances are, we now are ready to talk about how do we measure these large distances. Of course, we cannot take a scale that is quite long and then start measuring these large distances. That is quite impractical. What we do is that we use indirect methods to measure these large distances like your parallax method and so on. Suppose the first one, we want to measure the size of heavenly bodies. That means you have, let's say here, moon, and then we are here on earth, and I want to measure how much is the diameter of this moon. That means how big is the moon. For that case, we use two telescopes, or let's say one telescope from earth, such that from the first telescope we focus on the far end of the moon, and from the other telescope we focus on the other far end of the moon. Since these telescopes are present on earth, we can easily measure how much is the angle made by these two telescopes which are focusing these two far ends of the moon. Clearly you can see this diagram looks like an arc subtending an angle at the center, such that I have to call this as the radius, and this length or distance we have to call it arc length. The relation between the angle theta, the radius and the arc length we have already seen is theta equals to the arc length, that is your d, which here is a straight line, but since it's going to be very far, the straight line can also be taken like an arc. So we have the arc length as d, which is nothing but the diameter of the moon or the heavenly body. This d here represents the distance of the heavenly body, and when we use this, we have to make sure that the theta is measured in radians. So using this simple formula, we multiply this theta and this d to get this small d. Finding small d simply means knowing the diameter of this heavenly body. For this, we have to know how far is the heavenly body and how much is the angle subtended by the heavenly body. Next, if we are to find what is the distance of the heavenly body from, let's say, Earth or any other planets, we simply have to take again two telescopes at two different locations like your A and B, which are at a distance d on Earth, which we can measure because they are located on Earth. Then we have this heavenly body where these two telescopes are being focused or seen looking at, such that the angle made by these two telescopes at this point, which is taken as the center, is theta. So we take this distance as d, the distance between the heavenly body and the Earth. This small d is the distance between the two telescopes that we are going to fix it on the Earth, and this is theta is the angle made at the center, which is the heavenly body, by these two lines that we have from the telescope. Knowing this theta, which is an angle and that can be measured easily, this d here, which is the distance between the two telescopes on Earth, which again can be measured easily, we can find how far is this heavenly body is. That means we can find capital D. For that, again we use this formula, which is the relation between the angle theta, the arc length, which is your small d, and your capital D, which is now here the radius. So we write that, and then simply we write capital D, which we are finding right now, should be equal to small d divided by your theta. Based on what you have learned just now, we can solve some numericals now from your NCERT textbook. The first one is your example 2.3. The question is, the moon is observed from two diametrically opposite points A and B on Earth. That means we have the moon and we are looking at the moon from two diametrically opposite points A and B on Earth. That means we are looking at moon from here, we are looking at moon from here. The angle subtended at the moon, that means this angle here, has been given to be 1 degree and 54 arc minutes. Given the diameter of the Earth to be about this much, 1.276 into 10 to the power 7 meters, we have to calculate the distance of the moon from the Earth. That means we have to find this capital D, which is the distance between the Earth and the moon. Now they have given all the things that we need, and we know relation between this angle theta, between this distance capital D, and this arc here, which is your AB, that's your small d. We can write theta equals to the arc length, that is your small d, divided by capital D. And from here we simply have to find capital D, which is simply your d by theta. but obviously we can use this formula provided our theta is known in radians. Right now, the angle is given in degrees and minute, but not in radians. So we write 1 degree is simply 1 degree, 54 minutes is simply 54 divided by 60 degree. We have converted the 54 minute or arc minute into degrees by dividing by 60. Then when I add this and this, we get 1 degree plus 0.9 degrees, and when we do that we get 1.9 degrees. This 1.9 degrees is the measurement of the angle in degrees, still not in radians. So we take that 1.9 degrees and we multiply by pi by 180. Now this is converted into radians. So we have got our angle in radians. This number comes out to be 0.0331 radians, which we can also write 3.31 into 10 to the power minus 2 radians. Here we have used the value of pi to be equal to 3.14 to get this result. Once we get the value of theta, we are now ready to use this formula, that is your d by theta, to calculate the value of capital D, which is the distance between the moon and the earth. We simply plug in the value of small d and theta that we have got just now, and we are going to get the answer in meters, because your small d was given in meters. Next we have a similar problem, example 2.4 from your NCERT, which you can do as your assignment. So you can pause the video and do this as an assignment. The idea here is that they have been given an angle 1920, which is your theta here. You simply have to convert this 1920 arc second into degrees. First you divide by 60. If I divide by 60, this arc second will convert into minutes. Again, if you divide by 60, then it will become degrees. It's like you're dividing by 3600. Once you get in degrees, again you convert that into radians and use the formula that you have already learned before. Next we have a similar problem again, where they have given the planet Jupiter is at a distance of 824.7 million kilometers from Earth. So we have Jupiter, we have Earth, and the distance has been given, that is your capital D. Its angular diameter simply represents how much angle is the diameter of Jupiter is making. So that is known as what is your angular diameter, and that is given to be 35.72 arc seconds. Since this is arc seconds, we are going to divide by 60 and 60, that is your 3600, and we are going to get in degrees. Once we get in degrees, we multiply by pi by 180 to get the angle in radians. Once we get the angle in radians, we use our usual formula that we have, that is the angle, that is the relation between the theta, the capital D and the small d, and from here we can find the value of small d. Now that you have learned about your fundamental units, let's quickly talk about your derived units. Suppose I am finding speed of a body. For that we have to use a formula that is your distance by time, such that for distance we know we can use a unit like your meters, and for time the unit is your seconds. Now clearly speed of a body does not have a unit of meters or seconds, but it is meters per second. So I can tell you speed is a quantity which is using a unit of your length, that is meters, and of your time, that is your seconds. That's why the unit for speed will be known as derived unit, because it has been derived or obtained by using the units of fundamental quantities like your length and time. So any unit that is derived from the fundamental units, or that is obtained from the fundamental units, we are going to call it as derived units. For example, again, if I am finding energy, let's say kinetic energy, the formula is half mv square, such that half we write half, mass will be measured in kilograms or kg, velocity or speed is measured in meters per second, then we have a square here, such that the unit of kinetic energy will be not half, of course, half is not a unit. So we get kg meter square seconds minus 2. This is, again, I can call it as a derived unit. That means your kinetic energy or any energy will have derived units, not the fundamental units, because you are using your unit of mass, unit of length and unit of time to get the unit of energy. So your kinetic energy is not a fundamental, does not have a fundamental unit, but it has derived units.